Okay, just to give you a bit of quick feedback on the recursion on integers exercise, I thought I'd run through Fibonacci and then the cutting up pieces of paper. So the Fibonacci sequence is given, I mean, some people start at 0, some start at 1, I'm going to start at 0. By the sequence 0, 1, and then the remaining elements of the sequence are given by adding the previous two. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, and so on. So to describe these by a function on integers, we say fib of 0 is 0, fib of 1 is 1, and fib of n is fib of n plus 2 plus fib of n minus 1. Sorry, I should have said n minus 2 there. Now, we haven't checked that n is greater than 1, which we should do, but I'm assuming we're not going to call it on negative numbers. So there we have our recursive definition, quite straightforward. If we take that definition and calculate the fourth Fibonacci number, fib of 4, what happens? Let's have a look. We'll be using this final clause here, so that says it's fib of 2 plus fib of 3. But then if we dig into the fib of 3 there, we find that that itself is fib of 1 plus fib of 2. So you can see that this is not going to be a terribly efficient calculation because we get that fib of 2 evaluated twice. So a bit later on in this section, we'll look at a more efficient way of calculating Fibonacci numbers. And there's a whole range of different ways we can do that. But just to be aware that the recursion of this form isn't always as efficient as... It's not always the most efficient mechanism. But again, just look at that description at the top. That says precisely, that's the declarative description. The first two Fibonacci numbers are 0 and 1, and you get the remainder by adding the previous two together to give you the next. That's it. You know, that's, okay, written in a mathematical style, but that describes it precisely. So, what about cutting a piece of paper into pieces? Let's look at some examples. Well, if we start off with, we've got our piece of paper, got no cuts, we've got a single piece. What happens if we make one cut? We get two pieces. Good. What about making a second cut? We're looking for the maximum number of pieces here. So we don't cut along the same line again, but what we can get by this is 4 pieces. So there's a nice hypothesis here that what we're doing is calculating the exponential. So it looks like perhaps the next answer should be 8. Let's see. What happens when we draw the third line? What you can see is happening is that that line in general will cross the other n-1 lines, and it will create n new areas. So on the nth cut we get n extra areas. It's not an exponential despite the strong, well, no, not strong, just right, the suggestion it might be. What we get here is 7, and what we've done is we've added 3 to the previous result. So turning that into a recursion, we get pieces of 0 is 1, and pieces of n is n plus pieces of n minus 1. You can see the result here. You can see that that's precisely what's happening for n equals 3 in the diagram. Okay, so recursion gives us a nice way of solving problems. We can call things multiply, as we saw in fib. We can do all sorts of different patterns of recursion. But just to show that you can see this as a nice effective way of solving problems. Okay, so that's it. What we're going to look at is a different style of recursion next, and so we'll move on to that now.